Okay, so as a recap from yesterday, we have our periodic table. We've now seen that we have trends going to either of these corners. So we have our corner down here, and that was our big corner. We have our corner up here, and that's our smaller corner. I also gave you the idea of the snowman that you can use, where you have your snowman is sitting sideways, and you have your snowman that is right side up. And that's our trend for our radius, right? So just to make sure that you got it, let's just do a quick question. This says, which of the following neutral atoms are smaller? So we're going to look at aluminum or sulfur. So finding on our periodic table, we have aluminum right here. We have sulfur right here. So if you notice, we're in the same period going across. So remember, you have two ways to think of it. We can think about our snowman, or we can think about our corner. So between aluminum and sulfur, who is the bigger one? I'm sorry, who is the smaller one is what the question says. So the smaller corner is up here. So therefore, going across, we are looking at the sideways snowman. Sulfur is our smaller atom. So we'll go ahead and circle that one. And remember, it has to do with the fact that sulfur has more protons. So number of protons is your argument whenever you're going across. So when I have more protons, I'm pulling in like a magnet. All right, now gold or silver, who is smaller? So let's look at gold and silver. So right here, we've got, here is gold, here is silver. So we are looking at an up-down argument. So with our trends, once again, you can look at your snowman idea, smaller at the top, bigger at the bottom. So therefore, the smaller of these two is going to be silver. So we'll mark that one in, and remember that your argument for an up-down or the group kind of trends is that you have layers. And then finally, atomic number 19 or atomic number 35. So 19 versus 35. So let's go ahead and find 19 versus 35. So 19 is potassium, which is right here. And 35 is going to be over here, bromine. So 35 is over here. I am losing my highlighter. There we go. All right. So we have bromine over here. So once again, they are across from each other, meaning they're in a period. When we look at that, we look at number of protons. So atomic number 35 has more protons. They are in the same energy level, so that's why we can rely on that. So therefore, the smaller of the two is going to be potassium. So hopefully you've got that down. Continue to work on it. Again, this is the number of protons argument, and we're going to move on today. So today we're going to be talking about ionization energy and electronegativity. So we'll come back to those questions at the end. So ionization energy and electronegativity, let's start with the vocab. So ionization energy says that it's the energy needed to remove an electron from a gaseous atom or ion. I don't want you to get too focused or bogged down by the gaseous part. It's the energy needed to remove an electron. So it's the effort, okay? So effort needed. So you need to ask yourself, is it easy or is it difficult? And that's gonna be the primary question when you're asking about ionization energy. So once again, when you are looking at your periodic table, remember we're dealing with either layers as we move down the group, or we are dealing with number of protons increasing as we move across the periodic table. And the evidence of protons increasing is going to be that atomic number getting bigger as you move from left to right. So when we have more protons, I'm just going to add on to this idea, that means that we have more pull. So remember, this is the idea of that magnet again. With the layers, I told you guys to think about coats. So as you get layers, as we have more layers, that means we're going to have less pull because you're going to have more layers that you have to communicate through, right? So just like we wear a bunch of coats or jackets and stuff in the winter to keep us warm, we cannot interact with the cold because we have so many layers. okay? And as we have less layers, then that cold is definitely going to make us cold, so we shiver and all that stuff. So as we move down the periodic table, we have more layers, which will give us less pull. So I'll write that right here. And let me erase this real fast. Okay, there we go. So we got more layers, less pull. When we move across, we have more protons, we have more pull. Okay, so more increased protons, increase that atomic number as you move across, more pull. Okay, that's going to be important to you because we're asking ourselves these two questions. Is it easy to take one away or is it difficult to take one away? Right? So if I have more pull, that's going to be more difficult. If I have less pull, that's going to be very easy. Okay? All right, so electronegativity. Let's move on to the next word. Electronegativity says that it's a proper which measures the attraction of an atom for a pair of outer shell electrons in a covalent bond with another atom. So what that means is that when I have my two atoms and they're going to be forming a bond, they both have these little electrons on the outside, right? This proton, or the protons that are in the center of this one, are going to be attracted to their electrons, and the protons in this center are going to be attracted to their electrons. So what we're asking ourselves here for electronegativity is how much, once again, are they pulling? So pulling a lot or pulling a little? A good example of that would be like a tug-of-war game. So as you can see here, the dog right here is beating the cat, and therefore that would be a higher electronegativity than the cat has. Let me move that out of the way. We'll leave that right there. All right, so electronegativity is, are they pulling a lot or pulling a little? Now, this is still going to relate to our trends and the ideas that we keep coming back to, and where we have layers and we have more protons. So if we are pulling a lot, okay, if we have a stronger electronegativity, we're looking to have more protons and less layers. Because once again, we want those protons in the center, in the nucleus, to be able to contact those electrons very easily. So we don't want layers blocking that, and we want a lot of protons to pull in like a magnet. Now, the pulling a little, you're going to have less protons if we're looking at across the periodic table, and we're going to have more layers. So keep that in mind as we go to approach these. The big idea between these two, or about these two, is that I like to think of it as the love of electrons trends. And they both tend to work, for the most part, the same way. We leave out noble gases for electronegativity because they're mostly not bonding with anything. But for the most part, these are love of electron trends, which explains the other symbol that we have on that periodic table that I keep showing. So looking at what the actual trends are for this love of electrons thing, okay, I want to point out, first of all, on our little periodic table that I kind of keep showing, that you have, so we've already touched base on the radius one, so the one that we have a big atom and a little atom, but if you notice, there's also a picture of a heart. So we have a little heart, and we have a big heart. And that helps you remember that this is the big heart corner, meaning they love those electrons. They hold on so tight, which means it's going to require more energy to try to take one away. It also means that in a bond, it's going to attract it a little bit more than something from this corner. So keep that in mind as we kind of look at what the trends are that you've seen already on your web quest that you did. So, and that's also a really good resource to keep referring back to, just so you know. All right, so we've got ionization energy increases as the atomic number increases in any given period. So what that means is that as you move from left to right, you increase your ionization energy, okay? So that means you increase that love of electrons, okay? And so if I increase my ionization energy, that means that over here in this top corner, this means that it's going to require more energy. So higher ionization energy. This corner down here is your small heart corner. Okay, so this is your big heart corner. Small heart corner is down here, and that means that it's going to require less energy. So a way that I think of these is that the ones that are down here in this corner are basically like handing off their electrons. They're like, here, you can take it. I will pay you to take my electron. And that's kind of the way to think of that. It's down here in this corner, and all your alkali metals, they tend to give up their electrons a lot more than something that's over here in this big heart corner, okay? These guys are actually holding on to those electrons. Let me make that look like a heart, actually. But these are holding on to their electrons a whole lot more than things that are down here in this corner. Okay? Or the right-hand side of the periodic table is holding on a lot tighter than over here on the left-hand side of our periodic table. Okay? The reason why we are increasing as we move across is because of that effective nuclear charge, which, remember, is your number of protons. Number of protons increases. So we are seeing that our atomic number goes up. If we increase our number of protons, remember, you're thinking about the magnet. Okay, so remember, if anything going across, it has to do with the number of protons, and the number of protons we've already thought about as your little magnet. So higher number of protons, you think of a little magnet, okay? And so that is why we are increasing as we move across. So let's look at the next one. So we've got ionization energy decreases as atomic number increases down a column or a group. All right, so let's not worry about our atomic number increasing, because that just sounds like what we just did. But ionization energy decreases down a column or a group. So remember, when our decrease, that means that we're requiring less energy. And that is because we have more layers, right? So this one has to do with the layers part. So if I have more layers, that means it requires less energy, meaning it is easier, right? So I told you on the last slide, is it easier or is it more difficult? And so when we are going down the column, as we get to the bottom, it is easier to take one away than it is up at the top, okay? So just to make sure that we've got this, what we want to think of here is that as I move across, we have more level of electrons, or higher ionization energy. As I move down the periodic table, I get smaller, okay? And so on the last video, I showed you guys the snowman idea. So the way that we do this one is very similar, except this time we're going to look at a snow cone. So with the snow cone, if we tilt it sideways, so once again, this is how it is upright. If we tilt it sideways, you see that the bigger end is off to the right, and the smaller end is off to the left. And if you look at the up-down one, we have the bigger end is up at the top, and then the smaller end is down at the bottom. So the atomic radius was your snowman trend, and your ionization energy is going to be the snow cone trend, okay, or ice cream cone trend. Similarly, we have electronegativity, which what we talked about earlier was that it's going to be how much it's attracting another atom, or the electrons in the other atom, in a covalent bond. So meaning how much is it pulling, right? So we looked at the tug of war thing. And so so what we're looking at here for electronegativity is that it is going to increase as atomic numbers increase in a given period. Meaning, as I move from left to right, I'm going to increase. That sounds familiar. That's just like ionization energy, okay? As we move down a column or group, okay? As we move down a column or group, we're going to decrease. Now, sometimes the words decrease and increase are kind of giving us issues. And so remember, focus on what are the big ends. The big ends are going to be kind of help you, or the corners, right? So once again, on this little periodic table that I keep looking at, okay, you see that you have a big heart end and a big heart corner, and you have a little heart corner over here. So focus on those two corners as your extremes, okay? And just realize as I move across something that's in the same row, I'm getting to the bigger heart side. If I move this way, I'm getting to the smaller heart side. If I go down a group, I'm getting to the smaller heart side. If I go up a group, I'm getting closer to that bigger heart side. Okay, so keep it simple. Think about two corners rather than increasing this way and decreasing that way and all that stuff. So in my opinion, that's honestly going to be the biggest help. So just a reminder, it's kind of like the last one, so I'm not going to go too much into detail, but as you're moving across, the whole idea for that is that you're increasing your number of protons, right? So if I increase my number of protons, I wanted you to think about magnets. That means that they're pulling really hard, okay? So increase your number of protons, think about magnets, little magnet over here, bigger magnet on this end. As I move down the group, remember that we have layers or shells. So layers, so if I have more layers, then there's less pull, because just like we wear a bunch of coats in the winter to keep us warm so that our bodies don't communicate with that cold, right? It doesn't interact with the cold. Just like that, with these atoms, as I have more layers, more shells, more levels, my electrons that are on the outside are not going to be communicating as effectively with what's on the inside. So more layers means shielding effect, okay? All right. So now let's try a couple examples. Make sure that we understand our love of electrons trend. Remember, I told you to think of this all as love of electrons trend. Okay? Okay. So we're going to focus in on that ice cream cone trend. So just to remind us, let me get another one over here. Okay, and so basically what we've got going on is that with this heart trend, or the love of electrons trend, remember that smaller end of an ice cream cone is down here. So if you notice, I have one ice cream cone or snow cone upright, right? So it looks normal. And then the other one, we're just going to tilt to the right. So just like our snowman trend, we have this ice cream cone trend. This is lower, this is higher, this is big. So big ionization energy. And this is going to be small or low. I guess I'll go low ionization energy. Okay. Again, this will be low ionization energy and big ionization energy. Okay, now what does that mean to us? Big ionization energy means it's more difficult to take one away. Low ionization energy means that it is easy to take one away. Okay, so big is difficult. Low is easy. So you're asking yourself, how easy is it to steal one of their electrons? Okay? All right. All right, so let's look at these examples just to make sure that we've got it. So we're going to focus in on number 4. Number 4 says ionization energy across a period. So we're thinking about going across a period. So is it easier to remove an electron from nitrogen or fluorine? So nitrogen or fluorine. So looking over here, here is nitrogen, here is fluorine. So if we were to zoom in so we could see their atomic numbers, we see that we have a 7 versus a 9. So the 7 means that you have 7 protons in the center pulling on those electrons. 9 means you have 9 protons in the center pulling on those electrons. So think about the magnet. Think about the idea that the 9 is going to be pulling a whole lot more than the 7 is. So therefore, which one is going to be easier to remove one from? And that would be nitrogen. Easier means less difficult, right? So the other way that you could have thought of this was using your ice cream cone idea, where you're looking at your ice cream cone that is laying sideways, because that goes across the period. Okay, fluorine is on this end, nitrogen is on this end. Which one of these is it easier to take an electron from? That would be the one with the low ionization energy. So let's go ahead and write our answer in for that one. So easier would definitely be nitrogen. Has less protons. For our next example, we're going to look at 5, ionization energy down a column. So now we're thinking about the up-down argument, which has to do with layers. The more layers that I have, the less difficult it's going to be for us to steal an electron from that atom. So looking at number 5, it says, is it easier to remove an electron from lithium or cesium? So lithium and cesium we've got over here. Lithium is up here, and cesium is down here. So we're looking at energy level 2 versus energy level 6. So 2 layers versus 6 layers. So looking here, you can kind of see that the radius is definitely different, but more importantly for ionization energy, we can see that if I have a little proton in the center and a little electron on the outside, there's a lot more things in the way, so this electron is not being held as tightly as one that would maybe be right here. So here's a proton here and a little electron here. This is definitely a lot stronger attraction. So that being said, which one is going to be, so the question is, which one is going to be easier to remove, lithium or cesium? Definitely going to be the one that has more layers, cesium. It has lower ionization energy. Okay, so the next question that we're going to approach is electronegativity. So remember, electronegativity is going to be the same idea in terms of it's the love of electrons. So remember, we're still following that trend with our hearts and our ice cream cone. So electronegativity is how much are they going to be pulling and attracting something. So same idea as ionization energy. So which one is more electronegative, sodium or chlorine? So sodium is going to be right here. Sodium's going to be right there, and chlorine is over here. So across from each other, we've got which one is going to be more electronegative. So we're looking at the bigger end, which would definitely be chlorine as our answer. So now we've gone over all the trends. Tomorrow you will get another short video that will review all of it, but just a reminder that the big ideas are that you have radius, which is the big corner versus the small corner. Okay, big corner versus small. And then you have the heart idea, or how much they love those electrons. So you have a little heart, big heart, little heart, big heart. And remember, for each of these, you also have your snowman idea that you can definitely refer to. Remember, it's either upright or it is off to the right, so tilting over to the right like you see right there. And then same idea with the snow cone or snow ice cream cone. You have it tilted over to the right or upright. So use those 2 ideas to help you with your practice today.